In advanced electronics and experimental fusion reactors, engineers use specific architectures to generate massive magnetic fields and keep that energy trapped in a confined space. This is the primary function of the toroid. Physically, a toroid consists of a single, continuous wire wrapped tightly and repeatedly around a hollow, ring-shaped core. Our objective is to calculate the exact magnitude of the magnetic field generated specifically inside the hollow space of those coils. Calculating this field using the Biot-Savart law requires solving highly complex three-dimensional integrations due to the curved geometry of the wire. Ampere's law provides a mathematical alternative that can bypass this complex calculus. This law only provides a clean solution when a system has a high degree of symmetry, a condition the circular toroid meets. This derivation uses the mathematical progression on the left and the physical model on the right to solve for the internal field. Before looking at the equations, we need to establish the physical geometry of this cross-section. The core is defined by two boundaries, the inner radius, R1, and the outer radius, R2. An electrical current I enters the system and travels continuously through the entire coiled structure. We define the total number of times the wire loops around the core as the variable n. By mapping these geometric variables to Ampere's law, we can transform a calculus problem into a straightforward algebraic solution. The first step in applying Ampere's law is defining an imaginary closed boundary, an Amperian loop, to evaluate the magnetic field. We can anchor this theoretical concept to our primary diagram. For this derivation, the Amperian loop is the solid yellow circle passing through the center of the toroid. We represent the radius of this specific loop with the variable r. The placement of this radius is mathematically precise. According to the definition on the board, r equals r1 plus r2 divided by 2. This places the loop exactly halfway between the inner and outer edges of the coil. Centering the loop within the symmetrical core ensures the magnetic field strength is uniform across the entire path. This is the full mathematical statement of Ampere's law. We will begin by evaluating the left side, the closed loop line integral. We evaluate this integral geometrically along our yellow Amperian loop. There are two vectors present on this path, the magnetic field vector, B, and the infinitesimal segment of path length, dl. At every point along this circle, the magnetic field vector and the path length vector point in the same direction. They are parallel. Because the vectors are parallel, their dot product simplifies from a vector calculation into standard scalar multiplication. Furthermore, the magnitude of the field B is constant at every point on this circular path, allowing it to be moved outside the integral. This leaves us to integrate the path segments, dl, around the full circle. The result of this integration is the total circumference of the circle, 2 pi r. By selecting a path that aligns with the field's symmetry, we have reduced the integral to a basic geometric product. Now we must evaluate the right side of the equation. The variable I sub e represents the enclosed current, the total amount of electrical current piercing the flat plane bounded by our loop. We can count this enclosed current directly from the diagram. The wire carrying the current wraps around the core in a continuous coil, passing through the plane of the loop multiple times. These loops show the wire punching through the enclosed area at the outer edge of the toroid. We defined the total number of these wire wraps as n. Since each turn carries a current I through the plane, the total enclosed current is the product of n and I. Substituting this into the derivation, the right side of the equation becomes mu naught times ni. This result shows that coiling the wire n times directly scales the source of the magnetic field. Note the notation on the diagram regarding the space around the coils. The magnetic field is labeled as 0 in the empty center, and 0 again outside the toroid. We can use Ampere's law to explain why these regions surrounded by current have no magnetic field. If we draw a new Amperian loop inside the inner radius, it encloses only empty space. Because this loop captures 0 wires, the enclosed current is 0, and the resulting magnetic field must also be 0. We find a similar result by drawing a massive loop that completely surrounds the entire toroid. This outer loop captures every wire turn twice. One half of each turn carries current flowing up through the loop's plane, while the other half carries current flowing back down. These opposing current vectors cancel each other out, resulting in a net enclosed current of 0. This proves the toroid's efficiency. It achieves magnetic confinement. generating a powerful field internally while preventing leakage to the exterior. We can now equate the simplified left and right sides of Ampere's law to complete the derivation. Dividing both sides by the circumference isolates the magnetic field magnitude, B. Look at the fraction in parentheses, the total number of turns divided by the total circumference. This represents the turn density, the number of wire loops packed along a specific length of the core. We represent this turn density with the lowercase variable n. Replacing the fraction with n gives us our final solution, B equals mu naught Ni. Mathematically, the interior of a circular toroid behaves identically to an infinitely long straight solenoid, with field strength determined by permeability, turn density, and current.